That's still the title. This is just the name of this particular work of art. Yeah. I haven't changed the name of my talk. This is so.
Well, that sounds much more interesting.
I know, right? Everyone wants a bowl of donuts. So I'm in the computer science department at the University of Connecticut. I work primarily. I have worked mostly in computational geometry and algorithms. I always feel a bit like a dilettante talking about topology. My daughter is the real topologist. This is her bowl of donuts, and she understood that somehow the bowl that holds donuts should also be a donut. Funny story, so when she was 3, she had this crown, this toy crown, and she put the crown on, and she said, "I'm the queen because I have a crown." And so I took a bowl and I put the bowl on my head and said, "Well, I have a crown too, so I guess that makes me the king." And she said, "No, silly." You know how like 3-year-olds say that? She says, and kids say the darndest thing. She said, "That's not a crown." I said, "Why not?" She said, "Its fundamental group is trivial." Kids are funny like that. Actually, that's not exactly what she said. But morally, it's what she said. Something about not having holes. And actually, that's not really, also, it's not really how the story went, because I didn't take a bowl and put it on my head. It was a basket. It was actually a basket. So if you look, actually, the basket had lots of holes, because it's where it's weaving. But we just put fruit in it, so I wasn't really worried at the scale of an apple. Those holes don't really matter. It's not like an apple is going to fall through the cracks between wicker in a basket. And I'm not going to engage in any extended metaphors, so at any point, if you want to figure out if that anecdote is related to the rest of my talk, you can think about that, but that'll be an exercise. I think maybe it is. It does. But this is my actual talk, which is, I guess I did change the title from what I submitted. I think I put the word scale selection in here too, which is a problem I'm not really going to talk about. And it's called sensors and samples, but I'm not really going to talk about sensors either. I'm going to talk about a problem which has the word sensors in it, but I don't think of it as a problem about sensors or sensor networks. I'm going to think about it as a data problem. This is joint work with my graduate student, Nick Kavana, and my undergraduate, Kirk Gardner. Actually, Kirk is going to start a PhD next year. Okay. So this is part of a larger project. I'm just going to list kind of what I see as some of the interesting aspects of topological data analysis. And in one slide version of what you might think about how you might think about these problems is that they're complex data problems. And complex, I mean complicated. I don't want to overload the word complex here, because we'll talk about complexes later. And they're collected somehow from a finite sample of an unknown space after undergoing some unknown transformations. And it's the challenge in topological data analysis, the biggest challenge you face all the time, is to figure out what hypotheses you could add to this setup to make any of the problems well posed. Okay, and so I'm going to talk about some of them. And we're going to focus sort of in this area here, is this question of looking at finite samples of unknown spaces. All right. And one of the simplest models you can use to kind of add structure to a finite point set is to say, look at a union of balls. Right, because just a set of endpoints has a topology of endpoints. It's rather uninteresting. But as you look at unions of balls of different radii, you can potentially see more interesting structure. Okay, here suddenly we see a hole where we didn't have one before. Okay, and the idea is just that, to fill in the gaps in the ambient space. All right. So one of the first papers that really brought these kinds of topology or homology inference problems to the attention of computer scientists, especially in the machine learning community, was this paper by Nyogi, Smale, and Weinberger. Really, you could think of it as 2 papers. And the idea was that if you have a smooth manifold and you have a sufficiently dense sample, that you could infer the homology of that manifold just from the finite sample, because in fact, this union of balls would have the same homology. In fact, it has the same homotopy type as the manifold. And so from an algorithmic perspective, you can actually compute something, because if you want to compute the homology of a union of balls, you can take the check complex, which is a simplicial complex which has one vertex for every one of these balls, and it has a simplex for every common intersection of balls. So if two balls intersect, there's an edge. If there's a three-way intersection, you have a triangle. In other words, it's the nerve of this collection of balls. And that's going to be, for a finite point set, that's a finite simplicial complex. You can compute the homology, and that homology is going to be the same as the manifold under some assumptions, right? In fact, they don't really answer some of these questions, but one of them is, well, what radius should you use? And the radius you need to make this theorem go through depends on how smooth, or how technically depends on the injectivity radius of this manifold. Okay, so it's also known as the reach, and I guess this same concept was invented several times, but it's the distance from the manifold that you get before the topology changes. Okay, and the other question that maybe comes up pretty soon is this smoothness really necessary? And Frédéric Chazal and André Luthier actually showed that the smoothness isn't so important. If you just have a compact set, you can infer the homology of this compact set. And the only assumption you need instead of the smoothness is that there are no critical points of the distance function nearby. So here's a set. It's a subset of RD. There's a function on all of RD, which is just the distance of that set. And there are critical points of that function. So, oh, here I've covered it with balls. So we'll say the critical point of the distance function is a point such that if I look at all the nearest neighbors, in this case there are 3 different nearest neighbors, if that point is inside the convex closure of its nearest neighbors, then it's a critical point of the distance function. Okay. It's what you naturally get if you extend the gradient of the distance to the areas where to the medial axis of the set. All right. And so they have this notion they call the weak feature size, which is the minimum distance over the whole set of the distance to its nearest critical point. Okay. And so as long as that's bounded, then in fact, again, where the radii are going to depend on this weak feature size, as long as the radii are sufficiently large compared to the sampling density, and it's a good sample, and sufficiently small compared to this weak feature size, then this union of balls will have the same homology as the underlying set. Except, well, not quite. It turns out that because if I don't have a drawing of it here, but here's a cartoon of it, it can happen that if you have a really sharp edge, that you get some kind of little spurious holes here. And so what they show is that if you look, instead of asking for just the homology of the union of balls, but the persistent homology of this union of balls into a larger union of balls, so I increase the radius, that the only things that will persist are the actual, correspond to actual homology classes in the set you care about. So although you'll get some weird stuff if you just looked at the union of balls, none of it will persist. Okay. Okay, so here's another paper that came out around the same time as, actually it's a collection of papers by DaSilva and Ghrist. But the one that I'm most interested in was their more general d-dimensional version. It came out around the same time as Frédéric and André's work. And they called it homological sensor networks. And the idea was they have some domains, we'll say just some compact set here, and it has some boundary B, and you have a collection of sensors, we'll call them P. And for now, let's just say they're all sampled somewhere in our set. And some of these, we're going to highlight some of these input points or sensors as what they call them fence nodes. These are the vertices that of the input that are sufficiently near the boundary. And I'm going to use this notation everywhere. If you see a set with a superscript, I mean the union of balls centered at the points in the set. with radius whatever the superscript is. So this P alpha is the union of balls of radius alpha centered at the points of P. This B alpha is the boundary thickened by alpha. So it's all the points within distance alpha of the boundary. And they don't assume they have any coordinates. They only have some neighborhood information between the vertices. So two vertices know their identities, and they know if they're within, say, some distance alpha over square root of 2, or they also know if they're within distance 3 alpha. So they need two different scales because, again, persistent homology is going to sneak in here. But their goal is to test if this union of balls covers the set. Again, almost. Instead, you get something like the set minus the thickened part of the boundary. So if I thicken the boundary and delete that from the set, I've sort of shrunk the set a little bit. And they'll at least get a guarantee that they cover the shrunken version of the set. All right, so D minus the thickened boundary is contained in P alpha, the union of balls. Okay, so this is a little bit different from those inference problems, because here what they're doing is they're actually checking if you have coverage, whereas the starting point for inference was assuming you have a good sample. How do you find the homology? Here we're going to try to actually certify and check that, give some guarantee that the set of points you have really does cover the set. Okay. Oops, did I say what they did here? Yeah, so in the end, the criterion they use is they check the d-dimensional persistent relative homology of some Rips complexes. So let me just remind you what a Rips complex is. If you have a finite metric space, a Rips complex, R alpha, is just going to have a simplex for every subset of points where the pairwise distances, say, are most 2 alpha. You may sometimes see this definition without the 2, but this is a more convenient one for relating the Rips complex to Euclidean geometry. Okay, so here it is in pictures. Here's a set of points. Here's a radius alpha. Since these balls intersect, then the distance must be less than 2 alpha. So I'm going to add some edges here. If I look at a larger scale, once I have all 3 edges, I also add the triangle. So it's also the clique complex on the graph formed by the 2 alpha neighborhood graph, if you will. And in fact, this picture is the right one to think about, where we're just going to have 2 scales. Looking at one scale into the larger one, and we're going to see what persists topologically between the 2. All right. And so here is a version of their theorem. I'm going to say it's based on their work because I've projected it into the vocabulary and a notation that I'm going to use for the rest of the talk. The idea is that if you have this connected set D, whose boundary is B, and in its boundary is a smooth manifold with injectivity radius at least 4 times alpha, then the d-dimensional homology of this inclusion of the pair of Rips complexes. You notice I've got the Rips complex at this smaller scale for all of the points relative to the Rips complex at just the boundary. If I look at it included into the Rips complex at the larger scale, again, relative to the Rips complex at the boundary, as long as if that turns out to be non-zero, then the shrunken domain, as the domain minus some thickened boundary, is covered by the balls of radius alpha. Right? So that's this is something you can compute here, right? Given just that little bit of information, even with no coordinates on the points, you can compute this. And if it comes out non-zero, then you have this guarantee of coverage. It could be that it comes out to 0 and you're still covered. But in that case, we can't. This topological coverage criterion just doesn't give you information in that case. All right, so here is a slightly more general version, where again you just have a set D and its boundary is B. I'm not going to assume that the boundary is a manifold at all. The only assumption I'm going to make here is that this map here at, in this case, the 0-dimensional homology. So the connected components of D minus the boundary thickened by 4 alpha, if I include that into the boundary into the set shrunk by only 2 alpha, as long as that map is an isomorphism. So if you want to visualize the set, I took the set D, I shrunk it by 2 alpha, and then I shrunk it by 4 alpha, and then I go back to where I only shrunk it by 2 alpha. It should be that all the connected components persist here. That I have the same set of connected components here. Okay, this is going to replace all this smoothness condition. And now what I'll get is, again, this is the same criterion, except, well, rather than just checking it's non-zero, I want that it's equal to the rank of J star. And again, I'll get the same coverage criterion. OK, so the shape conditions, which are the hypotheses we need to assume about the input in order to make a claim like this, we replace this smoothness with just something about the persistent homology of the connected components. Okay. And again, the criterion is really the same. If I assume that the set is connected, this will have rank 1, and so this will come out to be either rank 1 or 0, and it's this difference also goes away. Okay, so one of the first things we wanted to do was to try to figure out to what extent the geometric hypotheses were really necessary, and we found that in this case the smoothness was not so necessary, which was a bit surprising. Given that there's a bit of a discussion in the original DaSilva Greist paper that says that if you were to get rid of the smoothness assumption, that the constants would start to degrade and that it would get worse and worse. But in fact, it's not true, and you just need a different proof to see that. So we're going to call this the TCC, or the topological coverage criterion. Again, this is the algorithm. This is the thing you compute, and here is the kind of coverage guarantee we're going to get. Any questions before we go? All right. OK. So there are a bunch of key tricks, and these all come straight from Rob and Vin's paper. First, to use Alexander duality, which will allow us to take these questions about coverage and turn them into statements about connectivity. Obviously, we're going to use the nerve theorem to discretize the geometry. We're going to use Ripp's check interleaving. And that really allows us to work without coordinates. And finally, we're going to use persistent homology to eliminate noise or these kind of spurious features. And these, again, like I said, they were all used in that original paper. We're going to use them in a different order. And then we'll see how we can get not only the more general topological coverage guarantee that I showed, but also some other generalizations of this work, as well as a connection to the Chazal-Luthier result. Okay, so just a reminder about Alexander duality. Here it is just in the d-dimensional relative version that we'll use. So here I had I'm showing you a picture of the union of balls, but I'm going to write it in terms of the original sets here. So if I have the d-dimensional cohomology of our domain relative to the boundary, that's going to be isomorphic to the zero-dimensional homology of the complement of the boundary relative to the complement of the domain. And so in this picture, if this is the boundary, the blue and the yellow together form the complement of the boundary, and just the blue is the complement of the domain. So if I want to know about, if I expect D here is 2, so the two-dimensional relative homology here should be 1. It should have dimension 1, because that's like taking the domain and taking it modulo the boundary. So it takes this two-dimensional plane, it wraps around, identifies all the boundary as a point, and you get one bubble. And under the duality, that's like saying that I have I'm taking just the number of connected components here that are disconnected from here. And so if I didn't have coverage, forget about that for a second. If I didn't have coverage, so I would have some part of the interior here, which is blue, which means it's in the complement of the domain, or say complement of the covered region. And if this kind of pokes a hole in the bubble, or in the zero-dimensional case, it means that I have points in the complement of the boundary which are connected by a path to points in the complement of the domain. Okay. And so I just need to, I'm going to go through the specific proof of how this gets used, but this is the key idea, right? It takes coverage and turns it into connectivity. The next is this idea of interleaving rips and check filtrations. So the top line here you'll recognize, hopefully, as something like the topological coverage criterion, although this in fact is true for any dimensional homology groups. You can include these rips complexes into the check complexes. So the rips only use the pairwise distances, but the check was the full nerve. And there's a change in the coefficient, or the radius here. So I go from alpha over square root of 2 to just alpha. And these are all induced by inclusions. This all commutes. And this isomorphism here is the nerve theorem, which says that the check complex is isomorphic in homology to these unions of balls. And that isomorphism also commutes with these inclusions. That's sometimes called the persistent nerve lemma. All right. So the key takeaway here, though, is just that I can talk directly about the inclusion of this union of balls into the larger union of balls. And if I can bound, say, the rank of this map, I can use that to get a bound on the rank of this map. Okay, and vice versa, actually. It's more easy to say, if I want to know that the rank of this map is, in the end, I'm just going to bound the rank of this map. And it will tell me something about the rank of this map. In particular, I know that if it's non-zero here, then this must be non-zero. And so it really will suffice for us to reason directly about the offsets, which again is different from Robin Bin's paper, because there they try to use the embedding or the shadow of the Rips complexes as a proxy for the domain covered by the union of balls. But it's not necessary. You can actually, in fact, it's more direct to use the union of balls directly. Okay. So the other trick I mentioned is that we're going to use persistent homology. And in this case, it's going to be important to prove that any of the little extra or spurious cycles we find really are spurious and that they really will not persist. Okay. So let me give you the first idea of the proof. So I want to relate this union of balls to the domain. If I want to map between them, well, if I blow up the domain by 2 alpha, then I at least have an inclusion map. But the truth is, if I just looked at the points in the domain, you can't solve this problem because you don't know where the edges are. So we need to kind of consider also the boundary. So if I take this pair of spaces, this is the union of balls, and remember Q are the points which are sufficiently close to the boundary, I can include that into the domain blown up by 2 alpha and the boundary blown up by 2 alpha. Okay. So this is just an inclusion, and in d-dimensional cohomology, I'll get some corresponding homomorphism. And the first key idea is just that if this map is surjective, then I'm going to have coverage. Let me just actually, it's easier to see in under the Alexander duality. So if I take this map, it's dual to this one, and let's give it a name. Let's call it A star. This map is injective, implies that we're going to have the domain shrunken by 2 alpha is covered by P alpha. Question?
Why is your map on homology going in the same direction as your inclusion?
Did I do it backwards? Oh, I did it backwards. Shoot. Yeah, that's a mistake. That's a typo. Yeah. Good. But I think the bottom map, did I reverse everything? I hope not. It may be that I have a couple of these wrong then. Because the original, I took it from the paper, and when we first wrote the paper, we did it with just homology, and we did cohomology down here. So I apologize if that gets confusing. The key idea is just that if there's a point that's not covered, so it's in it's in the complement of P alpha, and it's also in the domain shrunken, that should be 2 alpha, then it's going to be non-zero in B2 alpha, D2 alpha complements here, because that's, well, this is isomorphic to, this is just, this is isomorphic to H0 of this space. This should be, again, I apologize, that's supposed to be 2 alpha. Okay, so it's some non-zero element, but since it's in P alpha, if I look at A star of X, it is just going to be equal to 0. So this is not new again. This is just straight from the DaSilva Greist paper in a slightly different different form. Okay, so if we want to check that this map is injective, or if we know that if this map being injective gives us coverage, that gets us part of the way there, because well, now if at least the space is connected, if it was also surjective, then we would be able to infer our coverage just by computing H0 of Q alpha P alpha. Okay, there's a couple problems here. One is that well, in general, it's not surjective, and this is where persistent homology comes in. It could be the case that here the circles that are empty are the circles, the coverage domain of Q. So these are Q alpha, and these are balls of radius alpha, and here's the boundary. And so this ball here, which is in P alpha, but it's not this point. The point corresponding to this is not in P. It creates a spurious relative 2-cycle. So this, if you looked at the nerve here, you'd see a square with one vertex triangulating it. Okay, but then relative to the square, that's going to give us a bubble. And you see, well, okay, I've drawn one that's small, but the challenge is to prove that all of them are small, and that any kind of one of these spurious features you might see near the boundary doesn't really persist. Okay. So, so instead of just looking at the inclusion from P alpha Q alpha into D2 alpha B2 alpha, we're going to look at the persistent homology here included into the persistent homology here. But like I said, we're going to do everything under through the Alexander duality, and so these are the maps we get. Okay. And so if we call this map J star and this one I star, and the map from the image of J star into the image of I star is just that map we get induced by the inclusions. We'll call that phi star. And just as before, if this map phi star is injective, then we're going to have coverage. And that proof is really this virtually identical to the one I sketched. And so here's the hard one, is to show that, well, if J star is an isomorphism, so if the connected components here are all persistent, right? Nothing is created or dies when I change how much I shrunk the boundary, then in fact phi star is surjective. This is equivalent to saying that that all of these spurious features that may have cropped up around near the boundary, that they all die as long as I increase the scale by enough. Okay, so here is a sketch of this proof. And so if I have a point x here, if I pick x to be in the region covered by the points, but not covered by the boundary points up to 3 alpha. So that means this point, you can think of it as generating a non-trivial persistent feature in the union of balls. So its homology class is in the image of I star. If it happened to be far from the boundary, then it would also just be, you could show directly that it's in the image of phi star. I should go back to the diagram. Excuse me. If it happened to be in here, then we would be able to, we know that x is also non-zero here, and we could just pull it back. So we know that under the assumption that J star is an isomorphism, then we can also pull it back to here, and we know that this homology class X is also going to be in the image there. So that case is sort of easy. The hard case is if we have a point which is actually close to the boundary, but we want to show that if it's close to the boundary but not, but in some kind of non-trivial cycle, that it has to be that this can't happen. Okay, non-trivial persistent cycle. And so there must be, since we assume it's close to the boundary, there's some point y here within distance 2 alpha. And so by the triangle inequality, this ball of radius 3 alpha doesn't contain any points of q, because we explicitly picked x to be within distance at least 3 alpha from q. And so this whole line segment from x to y is contained in the complement of q alpha. And since y is in the boundary, if y were in p alpha, then y would have to be in q alpha, because the only points of p that are within distance alpha of the boundary are in q. That was the definition of q, was to pick the points that were within distance alpha of the boundary. Okay, so we know that y, I think this is supposed to say, yes, I think one of these is supposed to be a not in. Yeah, so y is not in q alpha. Oh no, I'm sorry, it's in the complement of q alpha. Sorry, that's correct. And so, so we get that x actually, the homology class of x is going to be 0 in here, because this line segment itself is a singular one chain which has whose boundary is x, because y isn't being in p alpha bar is 0. Okay. This is so in one slide this sketches the whole proof. Okay. I'd like to show this figure. So in the DaSilva Greist paper, they say if you were to get rid of the smoothness assumption, the constant factors that you have to grow in order to kill all the spurious cycles would grow really fast. And the reason they thought this was that the way they proved it is, rather than proving something directly about the relative homology, is they looked at the long exact homology sequence, and they looked under the connecting homomorphism, and they tried to prove something just about the d-1 dimensional homology of just the points near the boundary, so just these points of q. And it's true. We worked out just a simple example where if I just looked at the homology, this picture, you should think of this squiggly line as the boundary of just a two-dimensional shape, as a subset of a shape in 2D, and these points of q. So now if I just looked at the one-dimensional homology, it's true that there's a very persistent one cycle that is just made up of points near the boundary. And this actually would break their proof, but it doesn't actually cause a problem for the topological coverage criterion, because although this cycle is very persistent as a one-dimensional cycle, it can't really form a persistent two-dimensional relative cycle, because I would need to have points which were outside here that were filling it in. Okay, because this would have to, in order for this to be a relative 2 cycle, I would have to have the inside filled in relative to this boundary. Okay. All right. So so that gives kind of a slight generalization of the topological coverage criterion, which gets rid of these smoothness assumptions. And one of the things we noticed as we did it is that it seemed to be very close to the Chazal-Luthier results. It seemed there was some relationship which we didn't quite understand. In particular, the Chazal-Luthier result was looking at almost the same inclusion of Rips complexes, but it had been explicitly designed to get rid of some smoothness assumption, whereas the homological sensor network paper said that smoothness was really necessary. And so once we got past eliminated that smoothness assumption, we tried to see to what extent we can line up these two results and see what their relationship is. And you see that they're really almost converses. So this is a lot of text, but let me walk through it because I think it's useful. So if I have a locally contractible compact set, and let's call it D, and B is its boundary, if this weak feature size is lower bounded by 4 alpha, and I have a sample P, and I have my points Q, which are the points of P near the boundary, then if I let HK be the homomorphism between, this is the pair, the union of balls, and relative to the ones near the boundary, included into the larger scale, if I look at that homomorphism, then I get the following two statements. The first one is really just an exercise from the Chazal-Luthier paper, which says that if you're actually sure that the entire domain D is covered by the balls, then the image of this homomorphism is isomorphic to this, the homology of the actual domain and its relative to its boundary. Okay, so you actually can, this is the homology inference part, where we're going to say if you have coverage, then you can infer the homology. And here is what you get from the topological coverage criterion, which says that if you just look at the d-dimensional homology here, if this is isomorphic to the homology of dB, then you have some other coverage criterion. So this one has the property that you're saying, if I have the homology, then I have coverage. But I only have to look at one of these, one dimension here. So they're almost but not quite converses. And we tried to put this to work. Here's the idea. If you take your point set P, and you subsample it to take only the points which are sufficiently far from the boundary. So UB is all the points that are farther than beta from the boundary. And I can now look at the homology of this subset U beta scale. Again, this is the offset, so it's the union of balls of radius gamma centered at the points of U beta. And I look at that included into U delta to the epsilon for now these constants beta, epsilon, delta, and gamma, where there's some conditions on how they're related. But if that's true, as long as the weak feature size is bounded, then you can get the dimension of the homology groups just from the rank of this map. And so what we're doing here is we're actually doing homology inference only with the weaker assumption that we only have this partial coverage. So if you're not covered all the way out to the boundary. And so you can combine the TCC with the topological coverage criterion to certify a coverage, assuming that you just know the number of connected components. Right, so if you just know the number of connected components, you can see if you've covered the rest of the space, at least most of it. And then you can from that, you can actually compute the higher Betti numbers by looking at the persistent homology of subsamples, okay, where you're just throwing out the points that are too close to the boundary. Okay. And one other neat side effect of this simpler analysis is that you can also prove bounds on, say, K coverage. So if I want to know not just whether or not the domain is covered by union of balls, but I want to know if I look at the space that's covered by at least K balls, if I want, I can get almost exactly the same proof. So here I've thrown some extra points in here, but it's I haven't changed any other part of the proof except to add some subscripts. Everything goes through exactly the same. And now all we need to say is that if there aren't at least K points in this ball, then there aren't at least K points in this ball, et cetera. Okay, so there, I'll just note in passing that you still need to replace that check Rips interleaving for K coverage. But I wrote a paper several years ago about a variation of the Rips complex, which also interleaves with the K fold cover version of the Rips of the check complex. So so you get K coverage almost for free. And it could be, this is work in progress, but we're thinking there may be some other interesting distance-like functions that you can swap in here in addition to coverage and k-coverage. Okay, that's all. Thanks.